次の講演は E.R. イトキンさんです。タイトルはバカなことはしないで、それはただの電球ですについてお話をいただきます。E.R. さんはチェックポイントソフトウェアテクノロジーの脆弱性研究者でいらっしゃいます。バグ報告、報奨金などセキュリティ研究の幅広いバックグラウンドをお持ちです。今回のテーマについて動画をいただいております。Our next session is Don't be silly, it's only a light bulb. Please welcome our speaker, E.L. Itkin.
Hello everyone, and thank you for joining my talk today called Don't Be Silly, It's Only a Light Bulb. Before we begin, just a brief introduction. My name is Eyal Itkin. I'm a vulnerability researcher working for Checkpoint's research group. And in my research projects, I tend to focus on embedded devices and network protocols, and in this research, I combine them both together. The motivation for this research started a few years ago, in 2016, when I heard of a new smart IoT device, smart light bulbs. I was already quite familiar with a range of smart IoT devices, even including a smart air conditioner, a device you can turn on your way home so the temperature will be just fine when you arrive. However, why would I need a smart light bulb? I only need a light when I'm physically in the room, and I'm fully capable of toggling the switch on and off when I enter and leave the room. Why would I need an app for that? And I figured out to myself, okay, if this is just a trend, people won't buy it, it will die out soon. And apparently I was wrong, because according to a report from the end of 2018, more than 400,000 households in the UK were already using smart lighting solutions, so people use smart light bulbs. Okay, but if I connect my light bulb to the Wi-Fi or to the internet, there'll surely be some security risk about it, right? So I went around and I asked a few people, and I always received the same response. Don't be silly, it's only a light bulb. It's fine. Obviously, I was not the first to tackle this issue, so we'll go on after a few prior work notable of discussing, which is a light bulb worm by Colin Flynn and Eyal Ronen presented their work on Black Hat USA in 2016. Later on, they developed the research into IoT goes nuclear, creating a ZigBee chain reaction. This time they were joined by Adi Shamir and Chior Weingarten, and I really recommend you reading more about their research on their detailed website. You really should read about the research because they actually presented a worth-flying demo from a drone in which they took over all of the smart light bulbs on campus. As both Eyal Ronen and Chior are old colleagues of mine, we together decided that with Eyal Ronen's help, I'm going to continue on their research and take it one step further. Okay, so what did they find? Well, the team of researchers found out that attackers can remotely steal a light bulb from a given ZigBee network and force it to join their own. Once it joined the network, attacker can transmit a malicious firmware update to the light bulb, thus fully taking over the light bulb itself. And if that wasn't enough, it turns out that even a regular light bulb can steal other light bulbs, and we don't need any fancy RF equipment, antenna, or anything of this sort. By combining all of these capabilities together, the researchers claimed that an attacker could take over a selected set of light bulbs in a given city. Each light bulb will take over all of the light bulbs in close proximity, and so on and so forth, effectively creating a nuclear-like chain reaction that will take over all of the light bulbs in the city. Sadly for us, the vendor fixed the last vulnerability, so we are only left with the first two. Putting that into action, we can see the following diagram. On the right, we can see a smart ZigBee light bulb communicating over radio with the bridge. The bridge is connected both to the ZigBee network and to the local network via an Ethernet cable, so that we will be able to control the light bulb from our mobile app. On the left, we can see the attacker. The attack starts when the attacker transmits ZigBee factory reset messages to confuse the light bulb and convince it to join their own network. Once joined the network, the attackers will transmit a malicious firmware update to the light bulb, thus fully taking over the light bulb itself. And this is where the original research stops. Our new goal is to infiltrate the network. Using the light bulb that we already possess, we hope to find and exploit a ZigBee vulnerability in the bridge itself, so that we will remotely take over the bridge. Once we took over the bridge, we're practically inside the local network, and we hope to trace and find local computers and hopefully even taking over them. Now that the attack scenario is plain, it's time to start. Some preliminary slides on ZigBee. ZigBee is a suite of high-level protocols for close proximity networks. It's an IEEE 802.15.4 base specifications that define a low-range, low-power radio. Not to be confused with IEEE 802.11, which is the more commonly used Wi-Fi. From our perspective, an additional information we should be aware of is that the maximum transmission unit, or DMTU, over ZigBee is only 127 bytes long. And I'll repeat that. The maximal packet we can transmit over the air will only contain up to 127 bytes. And with this harsh limitation, we should somehow still be able to exploit remotely a vulnerability we hope to find in the bridge itself. So it's going to be very interesting. Time to meet our target. Our target for this research is the Philips Hue smart lighting solution, now branded under Signify. In turn, Signify controls 1/3 of the market in the UK. As we described earlier, we're going to focus specifically on the bridge because the bridge is connected to both the network, both the ZigBee, the radio network, and the local network via an Ethernet cable. When tearing down the plastic cover of the bridge, we can see the following board. On the right, we can see the main CPU, which is a Qualcomm CPU usually used on Wi-Fi enabled embedded devices. On the left, we can see the ZigBee modem, which is an Atmel CPU. Like any other embedded device, we have a clear pinout for serial debug, which proved itself to be quite useful throughout this research. The main CPU is of MIPS architecture, and the operating system this time is Linux. Since in previous research projects we usually dealt with real-time operating systems, Linux is quite refreshing. Colin O'Flynn details in his blog exactly how to root the bridge, here on this link, and using the serial debug interface and a few glitches, we will eventually get a full SSH connection to the bridge so that we could extract the firmware and even upload our own GDB server to debug the bridge itself. As Ronen described when we first started this research, the bridge is using a single huge process that is pretty much doing everything. And this process is the IP bridge. The IP bridge acts as the brain of the device. It is responsible for both parsing incoming ZigBee messages, maintaining the protocol state machine, and pretty much everything out there that needs to be done. And like most embedded devices, the IP bridge is executed with root privileges, meaning that once we took over this process, we took over the entire bridge with the maximal available privileges. As you probably understood, this is going to be the target process for our research. Time to look for vulnerabilities inside the IP bridge. We started with the ZCL interface. ZCL stands for the ZigBee Cluster Library, which is responsible for managing the configurations of the device. ZCL exports a read attribute, write attribute interface, which is very similar to SNMP on traditional network-enabled devices. ZCL supports multiple types, such as booleans, unsigned integers of 8 bits, unsigned integers of 32 bits, and even dynamic arrays. Variable size data types in an embedded devices is a sure recipe for vulnerabilities, so this looks promising. Let's look how they implemented the parsing of incoming ZCL variables. We started by looking over the old firmware, which we inherited from the initial research. And we can see on the start that we are parsing a 1 byte lang field from the incoming packet. We allocate a fixed size heap buffer of 33 bytes, and then we read the entire blob into the heap buffer without any side checks. Essentially, we have a controlled 1 byte memcopy into a fixed heap buffer, And this is the definition of a heap-based buffer overflow. Sadly for us, this is the old firmware, when we still need to check the latest firmware to see if the vulnerability remained in the code. And of course it didn't. The support for array was dropped, and instead strings are used in the firmware. When parsing the CL strings, we allocate a new type of buffer, still over the heap, with enough bytes for all of our content, plus the additional byte for the null terminator. So there's no vulnerability in this time. As we can see, we still have new information in this updated firmware because now we have debug symbols throughout the entire firmware, which really helped when we reverse engineered the firmware. So the latest firmware version dropped support for the CL arrays, and instead the CL strings are supported, but without the original vulnerability. So it's time to search for other vulnerabilities. But wait, who handles the incoming ZCL strings after the initial parsing? After we dug in a bit deeper, we found the following code. And here we can find a fixed heap buffer allocation of 33 bytes, which is quite suspicious. And it is followed by an additional mem copy using the size from our incoming ZCL string into the buffer and without size checks. So essentially, this is the exact same array vulnerability we've seen in the earlier firmware version, just buried along the way. In order to read this code, we need an opcode stored in our struct, and the opcode should be 16. When we go back and see how the ZCL string was parsed initially, we can see that the opcode that was stored in the struct was indeed 16. It turns out that someone forgot to finish the migration from arrays to strings. Strings should have been marked with F, which later means that will be duplicated using strdup. And instead, it was marked as array with 16, triggering the old vulnerability that was still in the code, just buried a bit deeper. Now that we found a good vulnerability as a candidate, it is a good time to start transmitting ZigBee messages, hoping to trigger the vulnerability. When playing around with ZigBee, like the previous research, we chose to use the Atmega board. The Atmega boards enable us to send and receive ZigBee ready frames with raw format and whatever we like. They should be computationally equivalent to a Lightbulb, which is important because the original research showed that you can install our malicious firmware update over the Lightbulb, and if we will be able to implement our entire attack over this board, it means that we will be able to deploy it from the Lightbulb itself. And it turns out that timing constraints indeed dictate that we use C code executed from the board because we can't handle the delays from relaying the packet from the board to the laptop for further processing. And this meant that our entire ZigBee stack plus the exploit were indeed implemented in C, which took a while. And we found out that the vulnerable flow is accessible during a phase called commissioning. So what is commissioning? Commissioning is a process of pairing and associating a new light bulb into the network. There are two types of commissioning. We have classic commissioning and touch-link commissioning. In our case, the Philips Hue app for Android uses classic commissioning, and so we focused on this one. In theory, the ZigBee specs explain the entire process, and in practice, there's a lot of room for vendors to do as they wish with the standard. When analyzing the protocol, we found an obstacle. We couldn't find a documented flow of messages, meaning that we have the entire information for each message, but we don't know which message is supposed to be sent and when, as a response for what. So we're missing critical information here. We tried to sniff a full conversation from a legitimate Lightbulb and the IP bridge, but there are too many messages sent too fast. We couldn't track all of the messages and all of the flow. And if that wasn't enough, the initial messages in the commissioning are encrypted with a transport crypto key, a broadcast key that is shared between all of the ZigBee Lite devices. And we don't have it. Luckily for us, we're not the first to tackle this issue, and in this blog, there's a detailed explanations of all of the keys used during the commissioning, including the key itself used in the classic commissioning. So we extracted the key, added it to Wireshark, and now we're able to decrypt the messages we can sniff and encrypt our own messages. The analysis and implementation of the entire commissioning took a lot of effort, really a lot of effort, but eventually it worked. As you can see here, our board successfully masqueraded to a legitimate light bulb, which is a brand new checkpoint research light bulb with the model of CPR 123. It turns out that we can do the entire commissioning from our board, and we decided to open source our entire pickup with the classic commissioning on this link, so that other developers and researchers will be able to enjoy our conclusions. The lessons we learned thus far. Without user interaction, the bridge won't accept new light bulbs, which is a good security design. Still, we have approximately 1 minute to commission as many light bulbs as we want once the user told the bridge to look for new light bulbs. In addition, the user will only see light bulbs in the app after a certain phase, which we refer to as the ZCL phase. If we have additional light bulbs that won't reach this step, the user won't be aware of them. And the good news are we managed to trigger the vulnerability during this phase, so we indeed have a remotely exploitable vulnerability in the bridge. There's no state machine check in place. We can simply send whatever response we like, whenever we like. However, we need to do that during the ZCL phase. Time to start the exploitation. As we have a heap-based buffer overflow, let us focus on the heap for a minute. The bridge uses uclibc, or more specifically uclibc ng, which is an amended libc implementation aimed at slim devices without a lot of RAM and without a lot of CPU power. Essentially, it is micro-libc. It is much like glibc, but with way less sanity checks against a slim implementation, and essentially it is based on the dlmalloc heap implementation. All of our buffers will fall into the range of the fast bins, meaning that there is a bin for each buffer size in multiples of 8 bytes, starting from 16 being the minimal size. And inside each bin, we have a singly linked list of freed buffers. Our plan is to corrupt the singly linked list inside a given bin, so that malloc will be confused into allocate a buffer at an arbitrary address of our liking. When reading the code of free, we found out that when size is indeed small enough for fast bins, if the macro of fast bin index is used in order to find a suitable bin. In turn, fast bin index essentially divides the size by 8 and subtracts 2 because 16 should be the minimal size. However, there is no check in place that 16 is indeed the minimal size, meaning that if we corrupt the size of an adjacent heap buffer, upon free, we could get the illegal indices of -1 and -2. The index of -1 will store our buffer before the fast bins array and on top of the max fast configurable variable, which is too risky. However, the illegal index of -2 will store our buffer before the malloc state global variable and on top of an unused variable in the firmware address space. Essentially, we will create a singly linked list that malloc is not aware of and only free is using, effectively creating a ghost linked list which acts as a dev null fast bin. Once we have this bin, our heap overflow plan is as follows. On blue, we can see our buffer, and on purple, we can see an adjacent buffer that we hope will be a free one. Our plan is to modify only the size and the pointer of the adjacent buffer as so. The pointer will point at an arbitrary address, as we've seen earlier, and the size will be corrupted to be an effective size of 0 using the dev null fastbin, and 1 meaning that the previous buffer is still in use. Our heap shaping strategy will be, assuming we overflow the free fastbin buffer, we won. This is exactly what we aim at. We corrupted the singly linked list, and you will get a malloc-where location. If we overflow the use buffer, then upon free it will be inserted into the dev null fast bin. We won't see it any longer, and gradually we will shape the heap into the desired form. If we overflow the use buffer that lives forever, oh well, nothing bad really happened. And only in the last case, if we overflow the free large buffer, we actually will crash. So we don't want to do that. If done correctly, we will get the desired malloc-where primitive, enabling us to overwrite a function pointer and execute our shellcode, which is a good time to introduce the shellcode we decided to implement. Location, location, location. We need to store a binary shellcode in a fixed global address. And we only found one good candidate for such a buffer, being the ZigBee phonebook. The ZigBee phonebook is an array of ZigBee addresses seen by far or advertised to the bridge. It can hold up to 65 records of 16 bytes each, giving us an upper bound of approximately 1 kilobyte for the entire shellcode. When going over the neighbor record, we can see that the first 8 bytes are the extended network ZigBee address, which are fully controlled by an attacker, followed by an additional 2 bytes, which is the short network address, again controlled. And our stroke of luck ended because now we have 6 bytes of miscellaneous fields that we don't really control, which basically means that we have 10 controllable adjacent bytes out of each 16 bytes. And if that wasn't enough, the bridge is unstable when it gets more than 20 records. So our shellcode is going to be quite a small one. After a few failed shellcode attempts, we came up with the following plan. We will call mprotect to install a backdoor in RAM. The shellcode will fully restore the execution afterwards, meaning that we will restore the GOT and the heap. And the cost of the shellcode is only 16 records, which is well in budget, less than 20. If we look over a shellcode in IDA, it will look as so. The first record will execute a few assembly instructions and jump to the second record, which will execute a bit more instructions and jump to the third, jumping to the fourth, and so on and so forth until we executed our entire shellcode, restored the execution, and continued on as if nothing happened. If we connect all of the dots together, we can see that we start by commissioning a legitimate looking light bulb. After that, a fake light bulb will attack the bridge and install the backdoor. Now that the backdoor is installed, the legitimate light bulb will interact with the installed backdoor in the bridge and will deploy the payload, which in this case we decided that it will be Eternal Blue for attacking the computers inside the network. As we can see here, we dropped the file into temp exploit on the bridge, and it was executed with root privileges, which is a good time for our demo. Here we can see the user controlling the light bulb from the mobile app, even changing the color of the smart light bulb. Once the attack starts, the attacker will start by stealing the light bulb from the network and convincing it to join their own network. Once it joins the attacker's network, the attacker will change the color of the light bulb into a hideous color, so the users will notice that something is wrong with the light bulb, but they won't think that the light bulb is broken because then they will toss it away. Here we can see the user trying to fix the color of the light bulb, but to no avail. When looking in the app, the light bulb will be shown as unreachable, and the only way to reboot the light bulb is to delete it from the app and tell the bridge to search for new light bulbs. Here the attack starts, because we will masquerade to legitimate light bulb from our bridge. And behind the scenes, additional fake light bulbs will exploit the vulnerability, as we've shown before, and attack the bridge. Meanwhile, the user is happy because he thinks he has a legitimate light bulb, and now it works. Looking at on a different angle, we can see the bridge connected to the laptop and communicated over radio with our attacker. The attacker will exploit the vulnerability, attack the bridge, install Eternal Blue, and attack the laptop, hopefully popping a calc. And as you can see, the attack worked. The vulnerability was reported to the vendor on the 5th of November 2019, and the vendor issued a patch via an automatic update on January this year. You can read more about our research and the advisory of the vendor in our linked blog post. The official CVE for this heap-based buffer overflow is CVE 2020-6007. And if you happen to use smart light bulbs from Signify, you shouldn't worry. All of the products should have received the update by now. Conclusions. Even with an MTU of 127 bytes, ZigBee vulnerabilities are indeed remotely exploitable, as we demonstrated. Indeed, in addition, security mitigations only work when they are on by default. The IP bridge was a static binary using fixed addresses, without stack canaries, and with a writable GOT. And yet, there was ASLR for the heap, for stack, and for loaded libraries, and that's thanks to Linux. And last but not least, it turns out that smart devices are becoming popular by the minute, and yet we can't even trust our own light bulbs. Maybe we should do something about it. And with that, thank you for joining this talk.